Here we are with exercise 2 of chapter 14. And this is focused on what's called the economy, SVD, or singular value decomposition. And yeah, this is really just a compressed output of the singular value decomposition for cases where you have a really tall matrix or a really wide matrix. And the reason for this is that if you have a really big matrix and you want to get the full SVD or the complete SVD, then these matrices, the U matrix and or the V matrix, might be huge depending on how big the data are. But if the matrix, the data matrix, is very, very tall, so let's say, I don't know, 100,000 rows, but only 6 columns, then, U is going to be huge, but you don't really need it to be that big. So that's the idea of the economy mode SVD. So the idea is to figure out how to export the economy mode SVD in Python, in numpy, and then test it with tall and wide matrices. And now we're going to be using random matrices. So this is really just about looking at the sizes of U, S, or sigma, and V transpose. So the way to implement this in numpy is to add an optional input called full matrices. Now, by default, this parameter is true, but what we want to do here is set this to be false. And let's take a look at, actually, let me first set this to be true. Just to run this code, you can see you're just creating a tall matrix here, random matrix. We don't care about the numbers in this matrix. We just want to see what the sizes of these outputs are. A is 10 by 4. Here you see U is 10 by 10 and V transpose is 4 by 4. Okay, so now with that in mind, we can set this to be false. So now remember, U is 10 by 10. As I mentioned a moment ago, 10 by 10 matrix is fine. Imagine that this were a data matrix where you have 100,000 data observations and 4 features. Then that would mean that U would be 100,000 by 100,000. Now that is a really big matrix. Now we're starting to get into limitations of computation time and data storage and so on. Okay, so now if we set full matrices equals false, this gives us the economy SVD, also sometimes called the reduced SVD. And now you can see that U is the same size as A. And essentially what Python is doing is saying, well, only the first 4 columns in U actually get multiplied by a non-zero singular value. All the other columns are multiplied by a singular value of 0, so they just get zeroed out anyway. So let's just ignore them. Doesn't mean they don't exist. This is just a sort of convenience for computational simplicity that we only get back the first k columns of U. Okay, and V is still the same size because that is the smaller of these two sizes. So then what I would like you to do, or what you can try, is just changing the sizes. So let's make it 5 by 14. And now this is going to be a wide matrix instead of a tall matrix. And here you see that U is now its full size. So U is 5 by 5. And V transpose is now 5 by 14. Again, this matches the number of potentially non-zero singular values in A. And again, so this is 5 by 14, and now if we set this to be true, it's going to be 14 by 14.